Okay, welcome. Making a short video that will add a little, hopefully just 10 to 15 minute conclusion to the lecture that we taped last week. We finished kind of awkwardly without sort of one or two very important things. I'm not even going to try to blame that on someone else. I think we just ran out of time. So the last class, or what you were probably just watching a couple seconds ago, is what we proved is that if the second derivative of a function is positive, then f is concave up. And if the second derivative is negative, we didn't prove this, but the proof is exactly the same, then f is concave down. And this is great because it means that if we can analyze the second derivative of a function, then we can tell where the concavity changes, and that helps me graph the function. So we'll do one quick example. Let's take this function. Let's take the function f of x equals negative x cubed plus 3x plus 2. And this is a relatively simple function because it's a polynomial, and we already learned in pre-calculus how to deal with polynomials. And so we could probably make a pretty good guess about what this function looks like, but with calculus we can reveal its finer qualities. And also polynomials are kind of easy, so it's a good first example. Okay, what do I know about this function? Well, I'm going to take the derivative. So if I take the derivative, I get negative 3x squared plus 3. And though I could leave it like that, I would also want to know when this derivative is positive and negative. And so I'm going to immediately do some algebra on this derivative. I can factor out a negative 3, I get x squared minus 1. And in fact, this is negative 3x minus 1, x plus 1. Okay. While I'm at it, I'm going to take the second derivative. And what is the second derivative of this function? Well, now I'll go back to the most derivative-friendly form, which is this one right here. This turns out to be negative 6x. That's it, just negative 6x. Okay, cool. Okay, that's probably good enough for now. Alright, so what does this tell me? Well, what I'm going to do is I'm going to make a sign chart now. And I'll make a sign chart for the derivative of this function. Well, what does my sign chart look like? My derivative changes sign at negative 1 and 1. So I'll put in a little negative 1 and 1. It's negative, so it's like an upside down quadratic. So it's going to be negative, positive, negative. And what we learned is that if the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing, and here it's decreasing again. So I'm notating my number line. And then, this is kind of the new thing, I'm also going to make a graph of I'm going to make a number line of the second derivative. Note how I label my number line. And, what is this? It's going to change sign at 0. And not only is it going to change sign at 0, but because this is negative, it's going to be like an upside down line, so it's going to be negative and positive. And so from what I've just learned, I now know that the function is concave down here and concave up here. Okay, that's really cool. And now comes this sort of innovation which I got from this other teacher, which is really great. What we're now going to do is we're going to make an F number line. And the F number line is the F prime number line and the F double prime number line superimposed. Any point which is relevant on either of these two lines appears here on the F number line. So we're going to put in negative 1, we're going to put in 0, we're going to put in 1. It's important to be all neat and label the number lines and make it all line up properly. Well, what is going on here? The function is decreasing on the interval from negative infinity to negative 1, and it's also concave down. So now what we're going to do here is we're going to draw a generic decreasing concave down function. What does a generic decreasing concave down function look like? Well, concave down, hands on the elephant. If it's also decreasing, it must look kind of like that. Yeah. except I made this all wrong. That is because I made this number line wrong. Negative 6x is going to look like this. It's going to go positive, negative. Sorry if you were wincing in pain about that, but now it is fixed. It's going to be concave up and then concave down. Okay, so what that means is on the interval from negative infinity to negative 1, this function is going to be decreasing concave up. And a generic decreasing concave up function looks like this. I knew that it was a polynomial. It had to look like that. Is this right? Yeah. Okay. Then, on the interval from negative 1 to 0, the function is still concave up, but now it's increasing. So from negative 1 to 0, I'm increasing concave up. What does a generic increasing concave up function look like? Well, concave up, hands in the air, under the elephant, it's going to look like that. Okay. What does a generic increasing concave down function look like? If it's increasing and concave down, hands on the elephant, but increasing, and finally, on the interval from 1 to infinity, I'm decreasing concave down. So it looks like this. All right. A final thing that we can do, this is an optional step. You can't always tell when a function is positive and negative, but here I can. If we look a little bit at this function, we can kind of tell by sort of cheating when this function is 0. That's a little bit hard, but if I plug in a number, let's see, if I plug in negative 1, it just works, right? F of negative 1 is, negative 1 cubed is 1, minus 3 plus 2 is 0. So since f of negative 1 is 0, I can factor this. I have no quadratic term, 3, 2, and then it's like negative 1, that's 1, that's 1, that's negative 1, that's 2, it's negative 2, that's 0. It does go in. So it turns out that this function can be written as x plus 1 times negative x squared plus x minus 2 plus 2. So that's negative x plus 1 x squared minus x minus 2. Does that factor more? Minus 2 plus 1? Yeah. Hopefully I'm doing this right. Zoom, zoom, jump, jump, jump. Ooh, yeah, jump, jump. Okay, so that's negative x plus 1, and over here, this is going to be an x minus 2, x plus 1, I guess, right? X squared plus x minus, So this is actually just negative x plus 1, x minus 2. And is that true when I plug in 2 I get 0? 6, yup, and yeah. Okay, so this function has revealed itself to actually just be the function negative x plus 1 squared x minus 2. And I'm very comfortable graphing that function. I'm going to do that right now. Okay, so let's see, at 2, this function is 0. At negative 1, this function is 0. At 0, this function is 2. And what are some other relevant points? I guess at 1, I care about this function also. When I plug in 1, I get 4, I believe. Yep, so 3, 4. Okay, so I have my point 1, 4, I have my point 0, 2, and I have those 2 points. All right, and now let's see what calculus tells me about this function. It tells me my function is decreasing until negative 1, then increasing, which means I'm going to have a relative min at negative 1. So that is going to be a relative min. and then I know that my function is increasing and then decreasing again, so that tells me that at 1, there's going to be a relative max. It also tells me the concavity changes at 0, and that's kind of like the new thing. And notice how this work that we made analyzing these two number lines makes it sort of just play puzzle and put it all together. So what is going on with this function? It is decreasing concave up until -1. Then from -1 to 0, it's increasing concave up. And then, like, is this kind of weird point, it's hard to draw this, at which my function goes from being concave up to concave down. It's very subtle, and my picture is probably not that great. And then at 1 there's a relative max, and then my function is concave down forever, and it happens to also go through x equals 2. All right, this is a great graph of this function. Notice how if you had just given me this function in pre-calc, I would have basically given you more or less this sketch, right? It's going to be a double root at -1 and a root at 2, and it's going to be upside down. What I couldn't have done until calculus is to figure out that there is a relative max here. And what I couldn't have done until just today is to tell you that this is a special point where the concavity changes. And I think I haven't used this word yet, or else I did it just a second ago. But there's a name for this. This function is concave down, or concave up until 0, and concave down thereafter. So the tangent lines lie below the curve, and then suddenly at x equals 0, the tangent lines flip to being above the curve. And there's a name for this. This is called a point of inflection. All right. So let's just talk about this for just like a few minutes. What is a point of inflection? A point of inflection is just a place where the concavity changes. Is a place where the concavity of a function changes. So it's either where it changes from being concave up to concave down, or concave down to concave up. And every textbook defines point of inflection a little bit differently. That's because every textbook defines concavity a little bit differently. But essentially what it boils down to is there's a point of inflection when the second derivative changes sign. So we have a point of inflection when f double prime changes sign. Because the sign of the second derivative determines whether it's concave up or concave down, or indicates whether it's concave up or concave down. All right, before we move on, I just want to stress that point of inflection is not just a calculus term, but this is in fact a term that just people use all the time in life. And so just to be an educated person in society, if you read the newspaper, especially business section or anything about economics, you hear people constantly talk about the point of inflection. And so I just thought I'd tell maybe a quick story about this. So if we kind of make a picture of the economy, I've been telling this story since 2008. As you know, in 2008 there was a big problem with the economy. And now we're here in 2015, things have recovered somewhat. So let's see if I can tell this story. I don't know if it'll work or not. So let's make a graph. The y-axis could really be anything. It could be, let's call it just goodness of the economy. Maybe we'll call it employment percentage or something like that. Employment percentage. And I won't label the axis or anything. So here we were in 2008. Everything was great. The employment was really high, and then suddenly there was a crash. there was a discontinuity, you might say, or at least, well, something suddenly happened. And what started happening is, well, actually gets complicated to talk about this, but what happened is people started losing their jobs. And it went kind of like this. And everyone was losing money. Here we are in 2009. And things just got worse and worse and worse. So it's bad. The economy is like kind of in free fall. Now, what normal people might say is, man, when is the economy going to get better? And when the economy gets better is the point at which the employment numbers start going back up again. And we know that the employment numbers hit their low, or I guess unemployment hit their high, or employment hit their low. I actually don't remember. I want to say it was maybe like 2012? 2011? Something like that. I thought it was maybe 2011, just before the election. 2011, maybe 2012. This is when the country hit like maybe 10% employment. I thought that happened. I'm not really sure. And then things now have started getting better. And to the simplistic person, what we're looking at here is we would like to know when the country is hitting this low point, so that's how we know things are going to start improving. But economists are not interested when things start getting better, because they're trying to predict when things are going to start getting better. What they're interested in is when things stop getting worse. And so if you graph the rate at which we're losing jobs, it's going to look something like this is what actually happened. And now things are gotten really better, and I'm not really sure what's going on over here. But the key point of all of this rambling is that there's some special point, and the special point looks like, qualitatively just from my picture, right around here. This is the point of inflection of this curve. And notice that at the point of inflection, this is not when people start getting their jobs back. When people start getting their jobs back is down here in aggregate. What this is the place where the rate at which people are losing their jobs starts getting better. So this is not, this is the place, this is the worst place. This is the place when the rate at which things are getting worse starts getting better. And this is the point that economists care about, because it indicates when there's a point of inflection in some economic indicator, that means that the actual minimum is not too far away, and then things can start getting better. And in fact, this is a real thing. Every month, the government releases the number of jobs lost that month, and they'll publish, so you can calculate the rate at which the country is losing their jobs. And for a while there, in 2008, 2009, 2010, not only was the country losing jobs, which is another way of saying that this curve was decreasing, but the rate at which the country was losing jobs was faster and faster. We were losing more and more jobs per month at a faster and faster rate. And then suddenly, there was this point where we were still losing jobs every month, but the rate at which we were losing jobs started going down. And then eventually, the rate at which we're losing jobs is 0, and we start actually gaining jobs. Okay, so that's the point of inflection. Last, it is another thing that we really care about in a curve. All right, last little warning. Yes, I said that a point of inflection happens when the second derivative changes sign. You have to be a little bit careful about this. There are these functions like f of x equals x to the fourth, for example. What does this function look like? Well, we know what this function looks like, right? It looks like this, and there is no point of inflection in this curve. It appears to be concave up all the time, and I think that's borne out by the analysis. This is 4x cubed is the first derivative, and the second derivative is 12x squared. Now, it is true that the it is true that f double prime of 0 is 0. So just like critical values are the place where the first derivative is 0, and they might be relative extrema, places where the second derivative is 0 are things that might be points of inflection. So this is a possible point of inflection. But just because the second derivative is 0 does not mean that that it is a point of inflection. If you make the sign chart for f double prime, you see that 12x squared is positive on both sides. So indeed, even though the second derivative is 0 at 0, it's concave up to the left and concave up to the right. So there's no change in concavity. So there's no point of inflection. No point of inflection at x equals 0. So we have a special name, critical points, for places that might be a relative extrema. There's no special name for these points where the second derivative is 0. If you want to be cool, you could call them possible points of inflection. Okay, I think that is it. Good. Bye.